Okay. Whoa. It's a hot mic. Very, very hot mic. All right. We're going to go ahead and get rolling. I've got actually a lot of ground to cover, and I'm going to try to pack it all in and move through it pretty fast so that I don't make anyone late for lunch, and so that no one is tempted just to get up and walk out in order to get lunch. So my name is Zachary Cutlip, and I'm going to be talking to you today about reversing and exploiting BT wireless routers. I work for a company based in Maryland called Tactical Network Solutions. And at TNS, I spend most of my time researching and developing exploits and exploitation techniques targeting embedded devices and network infrastructure similar to the wireless router I'm going to talk to you about today. And specifically, the wireless router I'm going to be talking about is the BT Home Hub 3.0B. And this may be somewhat of an unfamiliar sight for people in the US, but this is actually one of the most widely deployed wireless routers in the UK. And it is issued to BT customers by BT. So this is the wireless router and DSL modem and broadband modem that is issued to BT customers. And so there's a picture of the Home Hub. And there's the backside of the Home Hub with your usual assortment of switched Ethernet ports, broadband port, DSL port, and whatnot. And I actually have with me, I've got a Home Hub that I bricked during my research, and I'm going to pass it around if anyone wants to look at it. You can take it apart and see what's inside. I just ask that it comes back to me eventually, after the talk. So the Home Hub 3B is made by Huawei. But to say it's made by Huawei is somewhat of an oversimplification. As is the case with a lot of these embedded devices, the chipset manufacturer actually does a substantial amount of the engineering for both the hardware and a substantial portion of the software stack that runs on the hardware. And in this case, the chipset manufacturer is Broadcom. So Broadcom has done a lot of the engineering in the Home Hub. And here's some additional kind of geeky details about the Home Hub if you care. But in particular, I want to call your attention to the fact that the Home Hub runs Linux. And this is interesting for a couple of reasons. One is from an analysis perspective. Once you actually get at the firmware and are looking at the individual binaries on the firmware, you're sort of interacting with a system that is that should be pretty familiar to you if you're used to working with Linux systems. The other thing is this is a relatively old kernel. So this is a 2.6.30 kernel. So many of the advanced, the modern protection mechanisms don't come into play until later kernels. So for example, we have an executable stack. And while the stack is randomized, nothing else is randomized, right? So there's no ASLR on the libraries or heap or anything like that. So it's only on the stack. When you log on to the web interface of the Home Hub, you actually see that there are relatively few configuration options, especially compared to wireless routers from other vendors. And in particular, I want to call attention to the fact that the firmware is entirely managed by the ISP. So there's no website that you can go to and download a firmware update file. And even if you had a firmware update file, there's no facility in the user interface to actually flash a firmware update file onto this device. So all of that is managed remotely by the ISP. Just want to share some backstory how I came to be investigating the Home Hub. So some users on one of the forums in the UK were wanting to hack their Home Hubs and unlock some additional configuration potential, right? Because it's not very configurable. And one user in particular emailed me, and he had seen me on the Hack5 podcast talking about hacking Netgear routers. So he emailed me and said, hey, we're trying to hack our Home Hubs and was interested if you would want to join in on the effort, right? And I said, well, okay, I'll tell you what, if you can ship me some hardware, I'll take a look, but no promises. And I kind of thought that would be the end of that, and then I wouldn't hear from him again. But he actually came through and shipped me a couple of Home Hubs. And so once I got the hardware, I logged onto the forum where the other users were talking about the Home Hub to kind of see where we were on the research. And it turned out that another user on the forum had already desoldered the flash chip from the home hub and extracted the firmware off of it, which gave us a really valuable beachhead to start analyzing this device. Because like I said, there's no firmware you can download from the vendor. Also, there's no serial port or JTAG that you can access on this device. So we had to start somewhere, and someone was able to get us the firmware off the flash chip. So the overall goal was to unlock the home hub and make it more configurable and maybe connect it to another ISP or possibly even flash a custom firmware to it like DDWRT. My immediate goal was to get an interactive root prompt. There are a lot of things you can figure out from static analysis, but there are some things you just can't, and it would be really valuable if we could get a root prompt on here some way to get a debugger on there and enumerate processes and what have you. Like I said, there's no serial port that we can do that. So I'm going to need to find a vulnerability that I can exploit. And it needs to be a kind of a low-hanging vulnerability because this is just the beginning of the research, right? So I don't even care if I need to exploit a vulnerability that's behind an authenticated web page. That doesn't even matter to me. I just need to get a root prompt, and I don't want to spend a lot of effort doing it. So some of the attack surface, and this is not a comprehensive list, but some of the attack surface I looked at included the web interface, which is arguably the most attractive attack surface, and in that it is the most user-facing, and in many ways the most complex attack surface. I investigated the UPnP service running on the device, and I spent a considerable amount of time investigating the configuration backup file, how that is created and restored, and I'll go into that in some detail in a bit. The first class of vulnerabilities that I looked for was a command injection. And a command injection vulnerability generally consists of some form of unsanitized input from the user, usually through the web interface, that is transformed into a system command, and it's going to be passed to the system function or popen function or some function that's going to execute the system shell. And they're relatively nice vulnerabilities if you can find one, because they're typically pretty easy to find. Usually just some strings analysis will turn up a candidate for a command injection vulnerability. And they're pretty easy to exploit. You don't have to do a lot of debugging, and they're not tricky to exploit like a buffer overflow. So if you can find one, they're pretty nice. They also tend to be very portable. So if you have the same device, say with different firmware versions or even different devices by the same manufacturer that has the same vulnerability, the same exploit code will generally work across all those devices and firmwares as long as the bug remains. They can be somewhat limited though. If you don't have useful commands on the system to execute, then there's not much you can take advantage of with a command injection vulnerability. So here's an example from a different device made by TrendNet. And what we have here is a ping command that is being generated dynamically. And then that shell command is being passed to system and is going to be executed by the born shell. And in order to exploit it, you just simply put a shell command in the field and submit it, right? And this is a really nice test, the reboot command, because it's immediately obvious if it works. Because if the system reboots, then guess what? You have a command injection vulnerability. So that's really all there is to it. So that's the first one that I look for, and you would be surprised at how common these are in embedded devices, especially consumer-grade embedded devices. So I generally just start with doing some strings analysis, and I look for printf-style strings that appear to be shell commands. And a kind of a giveaway for a shell command is it'll have a shell-style redirect, like this string that is redirecting to dev null. And then you need to verify which, if any, of those strings that you find are actually passed to a shell and which are combined with user-supplied input. On the home hub, there is an executable called CMS. And CMS gets executed by the web server over and over again to do a bunch of different things. And CMS itself executes a lot of system commands, such as IP tables. IP tables is actually an interesting candidate because oftentimes the portion of the web interface where you configure port forwarding rules, that will actually get turned into an IP tables command that gets executed by the shell. So we find a bunch of strings in the CMS executable, such as the ones you see here, and I actually found 189 strings containing IP tables. So there was one in particular that stood out to me, and it's this one right here. And among other things, it takes 12 different input strings, right? And I thought, there's no way that one of these input strings isn't coming from user input. I mean, there's like 12 different input strings. At least one of them is somehow coming from the web interface. In addition to that, it's got this shell style redirect. So I'm like, here we have a command that is being dynamically generated, probably from user input, and it's going to be executed by the shell. So at this point, I was basically done, right? I found my vulnerability. I just need to run it to ground, okay? So do we have a command injection? Well, do we have unsanitized user input? That can be a little hard to verify. If your input from the web interface is passed through multiple functions and maybe even across multiple functions along the way. Why do I keep cutting out? This is weird. The input could get mangled or sanitized or transformed in some way at any step along the way. So that can be a little hard to verify. An easier question to answer is, how does this command get executed? Is it in fact being executed by the system shell? It certainly for all the world looks like it's going to be. So when we do some static analysis on the home hub to see how that works, here's what we find, and here's a disassembly fragment of how commands get executed on the home hub. I'm going to explain to you what's going on here, so don't worry about it. So the first thing that happens is the command gets executed, or the command gets generated by SNPrintf, which in and of itself is a little atypical. Most of the time, the pattern that we see is a sprintf that's unbounded, which would make a nice buffer overflow, followed by a call to system. So the command string gets generated by SNPrintf. That string gets passed to the function QoSExec, and then QoSExec passes the string to the function ATPUtil exec command no hang. So the question becomes, how does ATPUtil exec command no hang execute commands on the system? Well, what I found is a little bit different than what I expected to find. I'm advancing through my slides too quickly. Crap. All right. Oh, still too fast. Come on. Learn how to work the computer. Okay. So the first thing that happens is the command string is parsed into an array, which is not what I expected to see. And then that shell style redirect that I said virtually guarantees that this command is going to be executed by the shell, the file referenced by that redirect gets opened. That's weird. Right. And then the process calls fork, and it calls dupe2 on the opened redirect. And then it passes the array that it parsed to execv, and then it calls wait for the forked process to finish. So what this means is there's no actual invocation of the system shell. So the thing that we said looked exactly like a system command that was going to be executed by the system shell actually never gets executed by the system shell. So that's pretty disappointing. Really thought I had a command injection vulnerability here. Turned out I did not. So one of the other things that I looked at, and I looked at a bunch of stuff, but one of the things that I looked at was the configuration backup file, and how does that configuration get backed up, and how does it get restored? And the configuration backup file represents a number of potentially interesting attack vectors. So for one thing, it is generally assumed to be well-formed, and it is assumed that it hasn't changed from what was generated by trusted code. So if that assumption is violated, that may lead us to some sort of memory corruption bug, like a buffer overflow or something. Further, in some cases, the configuration backup file will be parsed by a shell script when it is restored. And if that's the case, you may have an opportunity for command injection there, because it's very difficult to sanitize input in a shell script. Also, there may be configuration options in the configuration grammar that are not exposed in the user interface. So for example, you may have undocumented credentials. You may have the option to enable some sort of remote administration service like SSH, and that wouldn't otherwise be exposed in the GUI. So the configuration backup file is usually obfuscated in some way, mainly so that it's tamper resistant, so that the user doesn't dick around with their file and then restore it and then break their router and call technical support. Oftentimes it'll be encrypted in some way using either a well-known encryption mechanism or some sort of homegrown encryption. And then additionally, it may be signed to make it further tamper resistant. If they're using some sort of custom encryption mechanism, it's often not mindful of cryptography principles, and it may be simply a matter of reverse engineering the algorithm and re-implementing it in your own code, and now you've got a tool that will decrypt and re-encrypt the configuration file. On the other hand, if they're using strong encryption mechanisms, and the algorithms are sound, and the keys are well protected, then you're not likely to find a vulnerability here. And what I found was the home hub is using AES. Okay, so that's pretty good. AES is pretty sound, well respected. And I assumed that they were probably using per user or per device keys. And I almost didn't mess with it. I thought, this really isn't going to be worth my time. I'm not going to find a bug in their AES implementation. They probably didn't roll their own AES anyway. And in fact, if we go back and look at that, if you're familiar with some crypto libraries, those are actually polar SSL functions. So polar SSL is an open source crypto library. So I almost didn't mess with it. But then I thought, wait, now hold on a second. If I were to back up my configuration file, and then my home hub broke for some reason, and then they sent me a new one, I should be able to restore that config file to the new device, as long as they're the same model. And I had a couple of home hubs, so I tried it. I changed a setting on one, backed up the config, and restored it to the other. And it took it. It accepted the configuration file and restored those settings. And what this told me was that the firmware in one home hub has everything it needs to decrypt the configuration file from another home hub. And that also means that the firmware that I downloaded from the forum has everything it needs to decrypt the configuration file from another home hub. So I decided it was worth it to take a closer look at this API. And what I found was that the configuration file starts out life as XML data, and then it gets compressed by the Unix command gzip, and then it's AES encrypted, base64 encoded, and then digitally signed. Now, I don't know why it isn't digitally signed and then base64 encoded, because you end up with this 16-byte block that isn't base64, but whatever, that's what happens. Now, here's a disassembly fragment of the restoration process, and I'll go ahead and describe that. So first, the signature is verified and then removed, and then the rest of the process is just like you would expect. Base64 decoded, decrypted, decompressed. And it's actually a really straightforward API. And so I was able to simply declare those functions in a header file, and then write a little C program that calls the right functions to decrypt. And in fact, I just skipped the signature verification part. I was able to strip off the signature and then just pass the file to the decryption function and see if it would unpack my file. And then I cross-compiled that, and I attempted to run it in QEMU. And I linked it against libcfm API from the firmware, because that's the library that actually contains these functions. So I ran it in QEMU, and I ran into some interesting problems the first time I tried to run it. There were some dynamic linker errors. There were some functions that it couldn't find when I tried to run it. And it was interesting for a couple of reasons. One is they were really weirdly named, PZMM kfun2, for example. And the functions and the libraries on this system, the functions generally conform to a predictable namespace that is indicative of the library that they're found in. And there weren't any libraries that suggested they would contain a function called PZMM kfun2 or kfun1 or what have you. So the linker couldn't find these functions, so I went hunting for them on my own with some strings analysis, and I was able to find all the functions in a bunch of unrelated libraries, which was kind of the other interesting bit. All of the libraries that I found these functions in appeared to have nothing to do with configuration, import, and export. And it turned out PZMM kfun 1 through 4 build an AES key by poking static constants 4 bytes at a time into an array. And PZMM ifun 1 through 4 build an AES initialization vector in the same way, basically by assembling a constant set of bytes into an array. So I've located the functions, and I was able to get the libraries that have them loaded using LD preload. And I ran my program in QEMU once again, and this time I had success, which is arguably the first success I've had in this entire project. So that felt pretty good. And here's a fragment of the configuration file once it was decrypted. And as you can see, it's got pretty typical things in it, like IP addresses and the encrypted password for the admin user. The next step was to see if I could reverse the process. So I modified my config file, and then I, in my C program, called the encryption and signing functions, and then I uploaded it to the home hub. And that worked. It took the modification and applied those settings. So while I was at it, I had a program that I could run in a debugger and snag the AES key out of memory, partly because it's kind of sexy to snag someone else's AES key out of memory. Also because with the AES key in hand, I could now write a program that didn't depend on the firmware's libraries, and then I could compile that natively. And so then I wouldn't have to run it in QEMU. And also I snagged the AES initialization vector. Now, if you know a little bit about encryption, which is basically what I know, you know that the initialization vector should not be a constant value, but it is, and there it is. So AES key and initialization vector. So the next step was to see if there are any settings that could be placed in the configuration file that would unlock some configuration capability that's in the GUI. Man, this microphone is just wigging out. Okay. Okay. All right. Okay. So I did some strings analysis on the configuration API library, and I was able to sort of work out more or less the XML schema, or at least figure out what XML elements it's looking for in the configuration file. And what I found was there weren't any XML elements it was looking for that weren't already in the configuration file. And there weren't any options in the configuration file that weren't already exposed in the GUI. So unfortunately, I couldn't find any hidden settings that I could put in that config file and then restore. That's disappointing. Before I moved on, I looked at the default configuration file. And on the file system of the router, there's this default config.xml that is encrypted. And I was able to apply the same trick to it. And once I decrypted it, it had a ton more options in it, and had some remote admin creds that are presumably used by the ISP to remotely administer the device. Had a bunch of other stuff, but unfortunately, it was a completely different schema from the user configuration backup file, and it wasn't possible to modify it and upload it in place of a configuration backup file. So that trick didn't work. That was pretty disappointing. So I spent a lot of time figuring out how the configuration backup and restoration worked. And it was interesting, but ultimately didn't really yield me any access. So one of the things that I visited multiple times and left and came back to was hunting for some easy buffer overflows. And in Soho routers and other type of embedded devices, we often find just really stupid, simple stir copies and whatnot. And so I just didn't find very many on this device, which is really, really, really unusual. But I did find one exception, and there's this one program on there called BCM UPnP that used lots of sprintfs and stir copies and whatnot. However, BCM UPnP was really hard to analyze because it didn't disassemble cleanly. There were lots of functions that I couldn't find any cross-references to, so I couldn't find a code path that would get me into any of those dangerous functions. There were a lot of jump tables that didn't disassemble cleanly, so it was kind of a mess. And this is one that I got frustrated with and left and came back to multiple times. So I was going to need to dynamically analyze it somehow in order to find an interesting code path, since the static analysis was frustrated by the poor disassembly. So I would need to somehow run it in QEMU, and so I set up a QEMU emulation environment running Debian MIPS Linux, and I've got a tutorial for getting that set up yourself on my blog, and here's a link to it. And I will share this link and some other stuff at the end of the talk, so don't feel like you've got to take down the link. But if you want to get Debian MIPS Linux running in QEMU, I've got an article about that. So I had a lot of trouble getting BCM UPnP running in QEMU. And now BCM UPnP is a UPnP server that manages the wireless hardware on the device, and it's provided by Broadcom. So it wouldn't run in the emulation environment because it makes a lot of assumptions about the hardware that's present that clearly you're not going to be able to satisfy in emulation. It also makes a lot of queries to NVRAM for its configuration parameters, which again, your emulated environment doesn't have NVRAM. So the first thing I did is to write an NVRAM faker library. And you can download the source to that from my GitHub account. And I'll share that link again later. And my NVRAM faker library basically intercepts calls to NVRAM get. And you provide it an INI style configuration file that hopefully provides sane answers to those configuration parameters. You don't really know what the configuration parameters need to be because you don't have access to the device, but you can make educated guesses. So with NVRAM solved, I was able to get BCM UPnP up and running, but it would just idle. And when I would send msearch packets to it, it wouldn't actually respond to them. So I'm going to need to go back and do some more static analysis. What happened was when BCM UPnP starts up and it doesn't find any wireless hardware to manage, it sets some values in a global struct that I don't really know what they mean, but it basically those get set when there's no wireless hardware to manage. And so what I ended up doing was patching out the place in the code where it sets those values so that it doesn't modify them. So here's the before and after. So there it's setting the values, and then I just knocked out those values. So basically it leaves the initialized values intact. Okay. So once I patched the program, and I had faked in VRAM, I was able to get BCM UPnP up and running and responding to msearch queries. So that was pretty sweet. And once I did that, it was a relatively straightforward process to find a bug. And I found this stir copy, where if you send an msearch packet and there's a UUID in the search target, it'll stir copy the UUID onto the stack. And so if you provide an excessively long string in place of the UUID, then you crash the program. So here we see it looking for the UUID string, and if it finds it, it jumps down to this stir copy. Incidentally, this program is, like I mentioned, is provided by Broadcom, and I've found this exact same vulnerability in a bunch of other wireless routers since then. So if you're analyzing wireless routers and the chipset is made by Broadcom, this is a good one to look at if you can get the program running to debug it. So I wrote myself some Python code that would craft an msearch packet, and in place of the UUID, I just put myself a buffer overflow string. I sent it to the program, and we get this nice crash where we try to return to an address that we control. Sweet. There's been a lot of failure so far, so it's nice to have some success. Now, I'd like to talk at length about how buffer overflows work on the MIPS CPU architecture, but we just don't have time. So I'm going to refer you to a talk that I gave at Black Hat a couple of years ago where I go into that and more. So, and I'll share that link again at the end of the talk. Now, just briefly, I want to talk about a project that, that I've created that evolved out of this research and out of research that I've done into some other wireless routers called Bowcaster. And it's an exploit development framework. And it's not really a pen testing framework the way some other frameworks are. It's basically an API that you can use to describe your exploits. And when my colleague Craig Hefner and I started researching wireless routers, there just weren't a lot of good tools for exploiting these devices. And there weren't really any good payloads. Like there was one payload that sort of had made the rounds of the internet and was like on a bunch of different exploit sites, but it didn't really work. So I ended up writing several of my own payloads and my own encoder and a bunch of tools like that to basically make the process a lot easier. It's implemented in Python. It's really, really lightweight, just super small. And it's basically an API, among other things. It's an API that you can use to describe your buffer overflow strings. And like I said, it's got a number of MIPS Linux-specific payloads. And I'm currently in the process of adding some ARM support to it as well. And it's got a number of other useful utilities. Anyway, if you're curious about Bowcaster and you're doing some research into embedded devices, you can check out Bowcaster from GitHub. Okay, so it's time to, what just happened? So it's time to develop my exploit. So we've got a buffer overflow from a single multicast packet. Developing the exploit, as I mentioned, is made easier with Bowcaster. And I was able to develop an exploit that would give me a root shell via one of Bowcaster's connectback payloads. And I tested and developed this exploit entirely in emulation. Normally, if you have a serial port on a device, you can put a debugger on there and test the exploit against the live device and debug it that way. But I couldn't do that, so I had to test it entirely in emulation. And then, when I had it working, I tested it against the live device. And it worked and gave me root on the first try, which is pretty sweet. And, wow. I haven't even demoed the exploit yet, so that's awesome. Okay, okay, we're running low on time. Anyway, what this means is, what the implications of this are that you can find an exploit, test it, and develop it against a device that you do not have. There are so many embedded devices out there that I cannot possibly buy them all and develop exploits for them all. You know, I can buy some of them, test them, and return them to Amazon because I found a vulnerability in it and it's defective, but I can't do that to all of them, right? So being able to find vulnerabilities in devices that you do not possess is really cool. You can check out my proof of concept exploit from my GitHub project. There's this exploit that I'm going to demo and some others. But like they say, root or it didn't happen. So demo time. Now I'm going to put down the mic because I need my hands, but I'll just try to talk really loud. And if anyone can't hear me, let me know. Hacker's perspective and from an analyst perspective, right? Now if I want to interact with this device and debug processes and really see how stuff works, I can do that and have a much nicer environment. Is that a real show or is that still BusyBox? Yeah, it's still BusyBox. But it's my own BusyBox. So, and if you look at BusyBox, it's got like all the options turned on, which I think BusyBox is one of the coolest tools. So, okay, so that's that. cool. Right, so I'm rebooting the device and I'm waiting for it to like turn boot. But I also brought with me a couple more home hubs. And like I mentioned earlier, this is a multicast package, and I'm assuming this device. So some might say, well, that's a little contrived because who's going to have 3 home hubs plugged into their network? But like, what if this vulnerability worked in a wireless router? What if it was in an IP camera, right? And they're all in the same engagement section. So one of the modifications I made to Bowcaster just for this demo is a connect-back server that basically multiplexes multiple connections, right? So each connection and forward it to its own terminating server, right? So in this window, I'll throw the exploit and we'll start up the multiplexing server. And these 3 windows, I'll have 3 terminating servers that will each hopefully give me a root prompt. Start with that server, start with this server. Okay. And in this window, I will throw the exploit. Good. All the lights are blue. And fingers crossed. Additionally, there's the home hub 4 that's out now. I need to extract the firmware out of it somehow. But it's got this tiny little VGA flash chip that I don't have the gear to work with or mess with. Additionally, I don't want to break my home hub 4, and once I desolder the flash chip from it, then the home hub no more works. So I'm kind of holding out on that. Anyway, just some quick acknowledgments. My colleague, Craig Hefner, who's taught me basically everything I know about analyzing embedded devices. My company, TNS, pays me to hack on kind of whatever I want to hack on, which is awesome. And then these guys all helped me by either shipping me hardware or extracting the firmware off the file system, are also rather very, very helpful. So rather than throwing a bunch of links at you that you're going to want to write down or things like that, here's a blog post on my blog. And that has a bunch of resources. It's got my white paper, which has a lot more detail than I gave you in the slides. It's got a link to a video of my Black Hat talk. It's got these slides themselves and other stuff. So anyway, I can come back to this slide in a second if you want, but I also want to give you some contact information if you want to. That said, I think we've got maybe a couple minutes for questions for lunch. Okay, yes.
So you said you found some hard-coded admin credentials. Did you figure out how those were used?
So the question was, I found some hard-coded admin credentials, and did I find out how they were used? I think you're referring to the admin credentials that were in the configuration file that I decrypted. I believe those are used. This device is remotely administered by the ISP using TR069. I believe they use that to manage the device. Beyond that, I'm not really sure. There was a yes.
Yeah, you mentioned 8 weeks, but I assume you also do real work. Can you quantify like in hours?
I'm sorry.
Can you quantify how many hours you spend like working on things?
Well, fortunately in my day job, they let me pack on whatever I want. So this was my day job and my hobbies. So I was probably putting anywhere from 8 to 16 hours a day on this. So kind of what's personal time and what's work time is kind of a fuzzy boundary. So, but yeah, it was pretty hard.
Over how long a period?
About 8 weeks. Yes.
Why do people listen to that mic?
What's that again?
Why do people listen to me? It's on the application.
Well, so why were there so many symbols in the binary? There are a lot of things that are hard about reverse engineering MIPS Linux binaries, but one of the things that is easier is the fact that even when they are stripped, you still get a lot of symbols in MIPS binaries. I don't know why the MIPS GCC toolchain does that, but it does. Yes?
Yeah, you seem like you're pretty ninja at reversing wireless routers.
Okay, thanks, that's awesome.
Yeah, and I'm going to speculate, don't take this the wrong way, I'm going to speculate that you could probably pass the lifestyle poly. So what kind of home wireless router do you have?
The question is, what kind of wireless router do I have? And I get that question all the time. The truth is, we haven't looked at a wireless router at TNS that we haven't found bugs in. There are wireless routers that I haven't been able to analyze because I haven't found a good way to get at their firmware. But any router that we looked at that we can get at the firmware, we found bugs in. The wireless routers that I use in my house are Apple Airport Extremes, mainly because I just found they work well for me, not because I had any particular opinion about their security. So, were there other questions? Yes.
So did you decrypt any of the passwords with the admin credentials, or what kind of encryption? Was it a hash or was it actual encryption?
I'm actually not sure how those were encrypted. Yes. Yes.
So I'm a blue team guy, and
Okay.
you're obviously not.
Great.
From my perspective, what's like the one recommendation that you had for blue team people that are maybe designing or implementing these things?
Sure. Okay, so what would be a recommendation that I have if you're playing defense, right? So if you're if you're putting these devices on your network, if you're the user, do not enable remote administration. Okay, you can enumerate the crap out of these things on showroom. It is ridiculous what we can find. If you're designing one of these devices, one of the things I found out from BT, and I got to party with the BT pen testers when I was in London, is that these guys pen test the crap out of their devices. And I did not find the low-hanging fruit in these devices that I find in a lot of other vendors. And I wish we saw more of that internal product security pen testing from some of the other vendors. Yes?
Any indication that the latest gen of those systems may have patched the problems that you identified?
Yes. Yeah, so have they patched the problems that I identified? So as it turned out, BT actually discovered the same vulnerability I did. And they have worked with Huawei, and Huawei has worked with Broadcom, and they have now patched that bug in the later versions of this firmware. Furthermore, I have looked at other devices from other manufacturers where the chipset is manufactured by Broadcom. I looked specifically for that stir copy, and it is now a stir-in copy. It does copy bounce rate. Okay, so I'm being waved off for more questions, but please get in touch with me, talk to me at lunch or whatever.
Get around this.